Alright, today let's talk about something quite interesting. It's one of the foundations of how computer vision works. So today we're talking about this thing called convolution. If you're not familiar with the field of computer vision, you probably haven't heard of this term convolution before. Yet it's a really foundational building block of how image recognition in computers work, because it's such a foundational concept that was built up since the 1990s. It really popped off in like 2010 onwards, but really, convolution goes a long way back. It even links to how the human brain works, so I think that's pretty interesting. So first, let's talk what is a convolution. Let's have an example image. Let's say there's a person with a mountain in the background, and this is an image, and you know an image is made of pixels. So you can split the image into rows and rows of pixels. Split it into rows and rows of pixels and columns as well. Now, if you were to pass this into an AI model, you'd probably have to flatten it into a 1D like array or list of pixels. So it could be, this first pixel goes here, this second pixel goes here, and so on. And it's a very long list of pixel values. This is because computers work on basically algebra. You can't have 2D structure to algebra. It's like you have x1 plus x2 times like m2 for x etc. These values of x, they're all one-dimensional. As such, there will only be one-dimensional aspects to your data, which doesn't work for images because inherently images are two-dimensional. Like if the guy's face is here, let's say it's a smiley face, you can expect the pixels on top and below to be more important than those far away. But when you map it into a one-dimensional array like this, it's very difficult for it to make these assumptions. So what a convolution is a special operation, is a special thing that applies this thing called a filter. A filter is basically a matrix of special values that you apply to different patches of the image. What does that mean? I just said a whole bunch of jargon. So what does that mean? What it means that you have, let's say, a square filter like this. A filter just spans over a couple of pixels. It can be, let's say, 3 by 3, and you span a couple of pixels. So let's say I copy this over here to make it clearer. We have the filter, and we copy over a bunch of pixels like this. So let's say this is like half of my face, and you do a dot product. So both of these are kind of a matrix of values, and you know that with matrices you can do a dot product to get something sort of a similarity score. Matrices and operations are advanced math, but all you need to know in this context is you have two matrices, you do a dot operation, do a dot product, and can get how similar they are. So what this does is you can get the similarity of a filter with any part of an image. This doesn't sound like a lot, but if we go back, this actually unlocks quite a lot of different potentials. So let's say we have a filter that detects for vertical edges. So it'll values be something like this with nothing on this left and right, but the center part is fully filled out. So when we have a part of the image, which is, let's say, the side of my face, it's like this, let's say it's like an outline, you can see how the center and they deleted, my bad, the center and the part of the image here is very similar, and so the similarity is very high. What this means is when you get past this filter across the entirety of the image, you would get which parts of the image have vertical like stripes in them. In this case, the vertical filter. So it will look something like, so look at this sample image. You can see that the diagonal lines will have some vertical elements. So you can imagine those to be activated. However, at the top parts of the image, at the more vertical, horizontal parts like here, these are going to be less activated because they don't have these vertical spaces. So your final filter would look something like this. It highlights all the vertical components, but it would ignore all of the horizontal components. This is where you can see where you can check where there are vertical edges. And this may not be inherently useful, but imagine what this can do if you're not just checking for vertical edges. And that's what we're moving on to. So now you can see how a filter can check for similarity. Now we can check for not just abstract concepts, but for vertical, not just for abstract concepts, but for more like concrete things as well. So imagine the scenario. You have one set of vertical filters, just as so. Imagine you also had a horizontal filter that's something like this. So you have a horizontal filter, and you applied it to the image to get only the horizontal elements, something like this. Let's say now you wanted to check for circles. Let's say I want to check for circles in my image. I know a circle has vertical edges and horizontal edges. So what if I had a filter that checks for, I wanted to check for a horizontal filter on the top and bottom and a vertical filter on the left and right. It's now at this point it's not just one matrix, it's three-dimensional matrices because it's trying to check for one image that only contains the horizontal parts and one image that only contains the vertical parts, such as this one here and this one here. However, let's just draw it out as H and V for now. Then this filter, you can apply it to this set of images, and it will see that, oh hey, there's some horizontal here, some horizontal here, some vertical here, some vertical here. It perfectly fits our representation. And so for the final image, that part of the image would be activated. You'll see, oh, it detects that there's a circle in this part of the image. See how from building up smaller components, we are able to detect bigger components in an image. So we went from just, oh, I keep deleting things. We went from just vertical edges, and horizontal edges. Jeez Louise, why do they keep disappearing? So horizontal edges, and now we can even detect simple shapes like circles. And if you keep repeating this process, eventually filters are able to detect things like eyes, faces, wheels, and a lot of different other things. So a key concluding point is filters detect similarity, as I've said just now. And filters can also represent concepts. So concepts aren't just like edges and like abstract features. They can also be just things which are real. So that's the power of a filter. The filter is able to detect a certain concept in your image, and not just detect if it's there, but because again it's a 2D image, you can tell where exactly it is. And that's powerful because you're trying to tell a computer to find things in an image, and that is the core of computer vision. One last thing I'd like to talk about is the receptive depth of a filter. So let's say if an image here, let's say it's split into a lot of different pixels. Let's say there's 128 by 128. You apply let's say 3 by 3, let's just say 2 by 2 filter for math's sake. 2 by 2 filter for let's say edges on one side, and then yeah, let's just say that, and then you get a smaller image that's 64 by 64. Each of these elements, let's say 1 or 0 or like 0.5, shows the similarity to the filter. That's why it's smaller. So in that 2 by 2 area, let's say here, in this 2 by 2 area, how similar is the content to our filter here? That's the value that shows up. And if you repeat this concept, you apply more 2 by 2 filters. So you have a smaller and smaller filters, get smaller and smaller results. 16, so on. Finally, let's do 8 by 8, something I can actually represent. That's not 8 by 8, but yeah, that's 8 by 8. So finally, we get to something small enough, 8 by 8. And each of these, you apply simply, let's say, a 2 by 2 filter. Notice how the image gets smaller. Where do all these extra pixels go? That's the wonderful part. Observe. This one value here is the result of 2 by 2 values here. And these 2 by 2 values, each of them are from another 2 by 2 values here. And so you can see that in effect, this 1 pixel here represents 4 pixels here, which represents 16 pixels here, which represents 32 pixels here, which represents 64 pixels in the original image. So 1 pixel contains information from 16 pixels. And that is the condensation of features, and that is how, as I said just now, these filters are able to have abstract concepts, because not only can you see like the super micro level edges, you can slowly, as you go up with more pixels, more information, you can extract shapes, you can extract things like gradients, different things, and all in all, you get to represent not just a single shape, maybe multiple shapes, maybe circles, squares, eventually faces, eventually whole humans, maybe even like crowds, you know. So different levels of representation. For example, just 2 by 2 you can get a line, but maybe 4 by 4 you can get an edge, and like 8 by 8 you can get a circle and a circle. 16 by 16 you can represent a face. 32 by 32 you can represent a person, and finally 64 by 64 you can represent the presence of crowds. So imagine mapping these to the above illustration above. Yeah. You have small features, first of all, which slowly get transformed into larger, more dominant features, more abstract or more real features. I see that abstract and real are opposites, but abstract as in you cannot define what a crowd is, but real as in you know what a crowd is, in comparison to, let's say, an edge. An edge is a very abstract thing because you don't just look at the thing and say, oh, that's an edge. But back to the topic, see how such small details can actually, through convolution, represent the details of so many different things. And all in all, the AI will learn that these represent abstract concepts like crowds. So, a summary of what we learned what let's use this pen. We learned what a filter is. We learned that it can represent similarity, and we learned that they can represent different concepts, from abstract concepts to realistic concepts like eyes, faces, and even wheels. And we also learned this thing called the receptive field. A receptive field is the concept where smaller filters at the end can learn to represent very, very large patches of area because of the compounding effect of multiple convolutions. So the earlier filters may only recognize small things like edges, but after compounding so many different filters, you can also expect to represent things like the presence of very abstract high-level features like crowds. And that's it for today. Yeah, hopefully you understand a bit more about convolution.